Hello everybody. In this video we are going to focus on stratovolcanoes. Well, as well as cinder cones later on. But anyway, the second type of volcano that we need to know is called the composite or stratovolcano. And again, the shape is so different than shield volcanoes that we already discussed in the previous video. One of the things that we see here is the slope. Look at this. The slope of the volcanoes of composite volcano is very steep. As you can see here, it's very steep, much steeper than the shield volcano that I showed you in the last video. Okay, so the characteristic is that it is large and it has a conical shaped volcano and it has a steep slope on its flank, and it is mainly composed of interbedded lava flows and pyroclastic debris. Okay, so as you can see here, again, this illustrates the alternation between lava flows and pyroclastic layers right here. Okay. And the magma composition for, in previous video, I mentioned that shield volcanoes are mostly mafic. For this one, it is mostly intermediate to felsic in composition. Okay, so the magma composition is intermediate to felsic. So again, this is another beautiful example of stratovolcano. This is Mount Fuji in Japan. As you can see here, it has much steeper slope compared to the slope at shield volcanoes. Okay. Composite or stratovolcanoes, they are mostly located in along the perimeter of the Pacific Ocean, which is called the Ring of Fire. And again, this is an example for that, Mount Fuji. We also have in the United States, we also have a series of composite or stratovolcanoes. For example, we have Mount St. Helens, which is one of the most famous volcanoes on Earth as well. So this is the Ring of Fire that I have mentioned previously. As you can see here, these triangles, the red triangles that we see here in the perimeter of the Pacific Ocean, this is what we call as the Ring of Fire. And obviously we call it Ring of Fire because most volcanoes on Earth are located right here along the edges of the Pacific Ocean. Now, why that is? Okay, that is also a good or a really good question to ask actually. Why do we have most composite or stratovolcanoes located along the edge of the Pacific plate? And the answer to that, okay, this is another view of the Ring of Fire. And here is the answer to that question. The reason why we have most stratovolcanoes along the perimeter of the Pacific Ocean or in the Ring of Fire, the reason for that is because these volcanoes are associated with mostly convergent plate boundary. Okay, especially when you have subduction of oceanic crust or oceanic plate, that goes underneath a continental plate. So what happened here is that as this plate goes down, goes into the mantle of the earth, the plate will be partially melted. And the reason for that is because obviously the condition or the environment here in the mantle is very hot. Plus, we also have seawater that got mixed with the plate, the undergoing plate here, so it kind of helps the plate to melt, and the process will produce melts, and the melts will go towards the surface of the earth, and that is the reason why we have volcanic activity on the surface, on the continental plate right in front of the deep sea trench, which indicates a subduction zone right there. Okay. All right, this is another view of of a stratovolcano, which is in Japan, which is called Sakurajima volcano in Japan. And as you can see here, we have plenty of volcanoes in Japan right here. The reason for that is because right towards the eastern side of Japan, we have a major subduction zone associated with the Pacific Ocean, that the Pacific plate that goes underneath the Asian plate right there. Again, as I mentioned before, that the United States also has some active volcanoes. So, for example, in the Cascade Range in the western side of the United States, we have series of volcanoes, which is actually located right here. Okay, in the northwestern part of the United States, as well as the southwest of Canada. Now, the reason for this volcanoes to exist over here is they are mainly associated with the Juan de Fuca plate that goes underneath the North American plate. Again, it is related to subduction zone. Okay, so these are some examples of U.S. active volcanoes along the Cascadian range right here. Here is the Cascade Range volcanoes. We have Mount Baker in Washington right there near Seattle, all the way to the Lassen Peak right here in California. And I think I'm going to show you the example from Mount St. Helens in Washington State right there. And here is another view of how, okay, I'm gonna put my head down a little bit right here so everyone can see what happened here is that we have the Cascadia Trench right here that is associated with the Juan de Fuca plate that goes underneath the North American plate. Again, we have subduction zone. The subduction zone will cause flux melting right here, and this melting will produce magma, and that magma starts to travel towards the surface and create this series of volcanic activities on the surface of the earth. All right, here is Mount St. Helens, one of the shield volcanoes or stratovolcanoes. I'm sorry, not shield volcanoes, okay? Mount St. Helens is an example of stratovolcano that we have in the Cascade Range in the northwestern part of the United States. Here is Mount St. Helens in Washington. And as you can see here, there's a big opening right here, okay, on one side of the volcano. And the reason for that is because this is the view of it before the eruption. The reason why we have a big opening right here because Mount St. Helens erupted in the 1980s. And there was a very, very major eruption that occurred around that time. Mount St. Helens before eruption in 1980. And this is what happened in the 1980 eruption. So let's take a look. As you can see here, the flank of the Mount St. Helens started to collapse, and this collapse of material actually released a lot of pressure from underneath the ground, and that actually allows a big, violent explosion of Mount St. Helens within that year. Okay, so here is another view of how Mount St. Helens erupted at that time. All right, Mount St. Helens after the 1980 eruptions, and as I mentioned before, it actually caused a huge opening right on one of the sides of its flank. This is the aftermath of the 1980 eruption of Mount St. Helens. The surrounding forests are devastated, and lahar flows brings lots of debris everywhere, especially along the river path. And Mount St. Helens, even though we had a major eruption in the 1980s, but Mount St. Helens is still very active until today. For example, here we have 2004 eruptions. Even though it was not as violent as the 1980s eruptions, the 2004 eruption was still notable, and it has it mainly produces this, steam and ash flow. One thing that I would like to talk about is these domal shape that you probably notice right here in the center part of its crater. Now, this is what we call as the lava dome. Lava dome forms in the crater of stratovolcanoes or composite volcanoes. The reason for this is because, again, most of the magma composition or the lava composition in this type of volcano, it actually has a lot of silica. Remember that compositionally it is mainly intermediate to felsic, meaning that it has high composition of silica. Okay, it has a lot of silica within its magma on lava, and it makes the lava to be very viscous, the magma to be very viscous, and sometimes this very thick and very sticky magma, it simply plugs the entire system. Okay, it plugs the plumbing system of this volcano, and it creates a dome right in the center of its crater. Okay, and this could also lead the escape of materials from the lava dome, or the explosion of the lava dome, once it cannot hold the pressure from the bottom anymore, then it will just explode, and it could lead to violent eruptions. So here is the condition of lava dome in Mount St. Helens in 2005. Right here, this is in May 2005, and this is in February 2006. So look how, you know, within just a year, look how, notice how, the shape of the lava dome evolves, and they are very dynamic in terms of the change of shape in a short period of time. So people actually learn about this. The reason, again, as I mentioned, that you don't want to have the system to be plugged for so long, because it could lead to more violent eruptions. So people study about the shape, the change of shape of lava dome through time. Okay, so here are the different lava domes that form at different time right here, shown by this picture right there. All right, so composite or stratovolcano, they often produces material which is called the pyroclastic material or pyroclastic flow. These are hot gases that have been mixed with lots of things, including ash and other debris such as rocks and steam and many things. And they sometimes they can move downslope at speeds reaching 200 kilometers an hour. Okay, so what happened here is this ash, this convective plume of ash. Now the denser materials. So when it goes up towards the sky, the denser materials will start to fall off, and it will fall along the flank of the volcano, creating what we call as the pyroclastic flow. Okay, so again, here is another illustration here on the right side, that we have violent eruptions, and it produces lots of ash and steam. Pyroclastic material goes up towards the sky, and then the dense material, especially the heavy materials, will start to just collapse and flow along the flank of the volcano, and this is what we call as pyroclastic flow. So again, this is an example of pyroclastic materials released by one of the most active volcano in Indonesia, which is called Mount Merapi. And here is another view of how pyroclastic flows look like. And here, these are very, very hot materials, okay? And they can be very, very dangerous, okay? Because they can reach up to 1,000 degrees of Celsius. So here is another view of pyroclastic materials from Mount Pinatubo in Philippines. And as I point out here, sorry. So as I point out here, if you see this, you gotta run, run. And here is this is actually a video. I'm not really sure where this video is coming from, but it's probably from somewhere in Japan maybe. But as you can see there, it's very scary. When lava flows, it flows along the flank and it can reach up to hundreds of kilometers, 200 kilometers per hour. Look at that. There you go. All right, so pyroclastic flow and pyroclastic material and pyroclastic flow, they are very, very hot materials, and this is one of the most famous discovery, which is the discovery of the people of Pompeii. Um, so these are actually fossils of human. Okay, they these people have been preserved because of the explosion of Mount Vesuvius in Italy. So this is Mount Vesuvius in Italy right here. It erupted about 79 CE, and it produces major pyroclastic flow that kill almost up to 20,000 people of the people of Pompeii. And because it happens very fast, and I believe it happened at night as well when people were mostly asleep. So there were lots of casualties associated with these volcanic eruptions, and the huge amount of pyroclastic flow preserve most of the people of Pompeii in volcanic deposits. Okay, so again, this is the definition of pyroclastic materials: a mixture of ash, dust, rocks, and gases during explosive eruptions of stratovolcanoes. Remember, pyro means fire, and clastic means fragments. And then these materials can be classified based on their grain sizes. Okay, so the smallest one is called volcanic ash. And then after that, we have lapilli, and the larger ones are called blocks or bombs. So here's an example of pyroclastic material, which is the finest one, which is the volcanic ash, that mostly consists of fine dust and glassy fragments. So these volcanic ash is called tephra. Before it becomes solid rocks, okay, they are called tephra. But once they undergo lithification and become solid rocks, the rock is called tuff. Okay. So this is what volcanic ash looks like, and these people they're supposed to wear some protective equipment, maybe wear some masks. The reason why I said that is because these um, volcanic ash, they actually consist of glass shards, so they are very, very, very sharp. Some of the quartz crystals are very sharp, and you just don't want to inhale this volcanic ash. Okay, it's very bad. As you can see here, this is what this is what volcanic ash looks like under microscope. As you can see here, that the crystal is very, very sharp, and again, you don't want these things to be in your lung. This is pyroclastic materials. This is the tough rocks. This is the example of lithified volcanic ash, which is called tough once again. These materials are called lapilli. These are slightly coarser than volcanic ash. It has walnut-sized material right here, as you can see here. Compare with this with the scale that I provided on the picture. Okay, and volcanic bombs or blocks are the large size of volcanic or pyroclastic material. Okay, so these are blocks right here, and these are bombs. They are Again, these are the huge chunks that were released by volcanic eruption. Besides pyroclastic flow, stratovolcanoes or composite volcanoes also have hazards. One of the main hazards associated with it uh, also include volcanic mud flow or lahar. Okay, lahar is basically mud flow that are mixed with mostly volcanic material, such as those lapilli or volcanic ash, or even big blocks or bombs from the eruptions. Okay, and they can be very dangerous. So, for example, in Colombia in 1985, 23,000 people killed by volcanic lahar in Colombia. Okay, the anatomy of stratovolcano. One thing that I would like to point out is that we know a term which is called a crater. Okay, a crater is an opening at the summit of a volcano, which is relatively small, actually less than 1 kilometer in diameter. But sometimes you've probably heard about something that we call as caldera. Okay, a caldera is also a conical shape of feature in the middle of in the center of a volcano, but typically calderas, they are produced by collapse of massive eruptions. Okay, so calderas are typically much larger. Okay, and cover much wider areas compared to crater. So crater is relatively a small feature right at the peak of a volcano. But once these volcanoes erupted, undergo a massive eruptions, then it could actually release lots of stuff from its magma chamber. Therefore, as a result, everything just collapsed, okay? Creating a huge depression right in the middle. And this huge depression that formed after massive eruptions is called caldera. Okay, so here is an example of a caldera. So this is called Crater Lake in Oregon, but this is actually not a crater. This is actually a caldera because they form after a big eruption. Because this feature formed after a big eruption. Okay, so even though it is called Crater Lake, it's actually not a crater. It is a caldera. Okay. And the last type of volcano that I would like to mention in this lecture is called cinder cone. Okay, cinder cone is built from ejected lava, mainly cinder-sized fragments, and they are mostly loose fragments. And typically, cinder cone has a steep slope, and in terms of excuse me, in terms of its size, it is much smaller than stratovolcano and composite volcano, and way smaller than shield volcanoes. Okay, so these are very small volcanoes, and they frequently occur in groups. And this is an example of cinder cone right here in, I believe, in somewhere in the western part of the United States. And this is Paracutin volcano, also cinder cone in Mexico. As you can see here, cinder cones like to form in groups right there. Okay, Paracutin volcano, it has a 10-year eruptive style, 1,300 feet high, and began as fuming crack in farm field. Okay, so that's the picture of Paracutin volcano in Mexico. The reason why we like to highlight Paracutin as one of the example for cinder cone is because this is one of the most active cinder cones on Earth. Okay, so again, its shape resembles stratovolcano, but much smaller. As you can see here, this picture nicely illustrates the comparisons of the size comparison between shield volcano, composite volcano, as well as cinder cones. Cinder cones are very, very small compared to medium stratovolcanoes such as Mount Fuji in Japan, for example. And it's just so small if you compare to the large shield volcano in Hawaii. Okay, so cinder cone is the smallest among all the three types of volcanoes that we already discussed. All right, so I think that's it for this video, and I'm going to see you again in the next video. Bye bye now.